All right, so as we enter into Unit 2, we are going to be talking about math. More specifically, we're going to be talking about what you do with the numbers or the data that you have already collected. And we did a little bit about it last unit where we did like some averaging, but now we're going to work a little bit deeper with some of those things. So as we move forward, the first learning target or the first objective that we're going to work on is writing numbers in scientific notation or standard notation and common metric prefixes. Hopefully this is a review for most of you. My guess is that it'd be nice to kind of like have a little bit of a review and slide into the week instead of, because you had that long 3-day weekend. You know what I'm talking about? Anybody? No? Anybody do anything fun on the 3-day weekend? The answer is yes, you weren't here, so like that's clearly the thing. All right, now, scientific notation is used to represent numbers that are super duper 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 big and super duper duper tiny. Nobody wants to write, like this example here, 602 with 21 zeros after it. No one wants to write that number more than once, much less at all. So a lot of times we will use scientific notation as a way for us to represent that super large number. Also, 0.0000000000072. Nobody wants to write that over and over and over again. So basically what we end up doing is we just kind of like drop some things that we call placeholders and write it into scientific notation. In scientific notation, or the examples for a 602 with 21 zeros after it becomes 6.02 times 10 to the 23rd, and the 0.000000072 becomes 7.2 times 10 to the minus 12. Basically, with scientific notation, we remove those placeholder zeros so that we can identify more correctly what the value actually is without writing a lot of zeros and wasting a lot of time. There is a base unit, or there is a base component, and that base component will be a number that has to be between 1 and 10, and we'll talk about that in a minute. And then there's an exponent component, and the exponent component has to be a number, can be positive or negative, and we'll talk about that in a second, okay? But this is your basic format for any number in scientific notation. Now, when you put things into scientific notation, there are some pretty simple rules about it, and you may have been taught a couple of different ways how to do this. Most ways are correct, but here's how we're gonna try to attack it. Basically, if you're looking at a really, really big number or a really, really tiny number, you locate the first non-zero digit, and then you throw a decimal after it in the number. And once you've done that, you now have your base number. Then you have to figure out the number of places that we need to move the decimal in order to get the number to match that original value, and this becomes your exponent. Now, if you move your decimal to the left, the exponent is negative. And if you move your decimal to the right, the exponent is positive. Now, sometimes that gets confusing. So oftentimes what I have been in the habit of telling students is that if the number is bigger than 1, actually I should write this correctly, is smaller than 1, the exponent is negative. And if the number is bigger than 1, the exponent is positive. And that's just kind of how I look at it. So going back up to the numbers up above, right? If I go back up here, 602 with a whole lot of zeros after it, that's a number bigger than 1. That means the exponent has to be positive. a lot of zeros and then 7, 2, that number is really, really smaller than 1. That exponent has to be negative. And that's kind of how I see it. Now, somebody in one of my earlier hours also made this observation that I thought was pretty astute. And they said, if there's a decimal at the beginning of the number, the exponent is negative. And I think that tracks, especially if we go back up here. We see a lot of zeros and a decimal right at the front here, and then the exponent was negative. So I think that was pretty decent observational skills. So those are the three, I guess the three things I usually tell students about numbers in scientific notation. Now, there are 4 examples. And what I would like you to do is I would like you to go ahead and take a few minutes and do these 4 examples in your notes, and then we'll go over them together as a team. So do, please, these 4 examples as a team, and then we'll talk about it. So what ended up happening is that we're going to talk about these in terms of the values that you should have had. So the very, very first thing I would have done is I noted that this first number is less than 1. So that means that my exponent has got to be negative. And then what I usually do is I write, so I look for that first non-zero digit, and I see the first non-zero digit is a 3. So I put a decimal after it, and then I just write 240. Technically, you don't need to write the 0, but I do because it makes me feel better about it. And then I go back and I count the number of spots I move the decimal. 1, 2, 3, 4, right? So this becomes times 10, and it's to the negative 4 because it's a number smaller than 1, right? And then we have this next one, so we're going to do the same thing. We're going to go across, and we're going to look for a number, the first non-zero digit, which in this case is 6. So I'm going to put a 6, and I'm going to put a decimal. I'm going to put a 0 because it makes me feel better, right? And then what I'm going to do is times 10 to the number of places that I have to move the decimal to get to the 6. So we always know that decimals are like right back here, right? So we would go 1, 2, 3, 4, 5, 6. So this becomes 10 to the 6th because this number, as we might recall, is bigger than 1. So the exponent is positive. Now, a common thing that some students will end up doing is they will end up just like counting zeros. And so like in the case of the first one, if you counted zeros, you might have written 3.240 times 10 to the minus 3, and that isn't okay, or it's not right, rather. And in the case of the 6 times 10 to the 6, counting zeros might have worked out okay, but you still need to count the number of places you move the decimal. Okay. Also, we'll talk about that in a second. Okay, so now the next one says write the following numbers in standard notation. So the first thing I see here is there is a negative value there, right? That negative value tells me that the number is smaller than 1. So negative exponent means the number is smaller than 1. And if the number is smaller than 1, it has to start with a 0, right? So what I'm going to do is I'm going to take the 8.74, and it's times 10 to the minus 4. So I'm going to move it in the direction that makes the number smaller than 1. So I'm going to move it 1, 2, 3, 4 spots. Throw a 0 in there because it makes me feel better. And now I'm going to clean this up. So 0.123874. So far, so good? Does that make a little bit of sense? No, yes? Okay. The next one, I see that the exponent is positive, and if it's a positive exponent, the number is bigger than 1. And if the number is bigger than 1, I'm going to move the decimal, the number of the direction and the number of spaces that makes the number become bigger than 1. So 9.26, I'm going to move it 1, 2, 3 spots, throw a decimal back there. I'm going to clean it up, 9260 with a decimal, and it makes me feel better. Okay? Now, don't you ever like I just want to make this pretty clear. Like, I've been writing stuff in scientific notation for like 30 plus years. Okay? Because I'm that old. Now, with that in mind, when I do these problems, I still go through the process of doing the whoop-de-doos underneath. You know what I'm talking about? When you do it, it's like whoop, 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 whoop-de-doo. You know what I'm talking about? That's what it sounds like in my head anyway. So like I'm still doing that. And unless you got drafted by the math league, like the professional math league, and got that big scholarship, and like are going to be playing in the math Super Bowl in January, like I feel like you should use that tool of the whoops. You know what I'm talking about? No? Anybody here get drafted? I was an all-star. Counter. 2, 3, 4, 5. Tough crowd. Metric prefixes. When I was younger than you, I was told by the nun at the Catholic grade school that I went to that by the time I became an adult, number one, I would never have a calculator in my pocket, which that's a lie. And number two, I would be using the metric system for everything, also a lie, because we still use cups and quarts and pints and teaspoons and feet and inches. Stupid things like that drive me nuts. Like 1 mile is 5,280 feet, but it's also 1,760 yards. Like, why can't it just be something easy, like multiples of 10? You know what I'm saying? The metric system is a far superior system, and yet we Americans are like, the rest of the world uses it? How dare they? We are better than them. We're going to use our old standard system that us and like 2 other garbage countries use. And by garbage countries, I mean countries that haven't gotten with the metric system program yet. Enough pontificating, I digress. You need to know some of these. You need to be familiar with these metric prefixes. So here we go. Let's talk about them. You might be familiar with a prefix that is kilo. You might be familiar with a prefix that is hecto. You might be familiar with a prefix that is deca. Then we have the base unit. And then you might be familiar with a prefix that is deci. And then you might be familiar with a prefix that is centi. And then you might be familiar with a prefix that is milli. So what do these things mean? Well, the base can be like a gram. It can be a meter. It could be a liter. It can be a lot of things, but those are the ones that we're going to really focus on. Okay. Now, a kilo is the relationship of a kilo says that 1 kilo equals, sure, 1,000 base units. And 1 hecto equals 100 base units. And 1 deca equals 10 base units. See how easy that is? Everything is a factor of 10. So much simpler. We then have one base unit is 10 deciunits. We then have one base unit is 100 centiunits. And one base unit is 1,000 milliunits. Again, based on the powers of 10. It's not too bad. So the question that some of you are thinking is, do I have to memorize all of this? And the answer to that question is some, but not all. Okay. So, I know some of you are still writing, so I'm going to wait a second. So the three that you have to memorize, the three relationships that you have to memorize, are these three. $1,000 meters is equal to 1 kilometer. 100 centigrams is equal to 1 gram. 1,000 milliliters is equal to 1 liter. So, I mean, it could be like grams or milliliters, or I'm sorry, grams or liters or meters could be interchangeable here, but it's kind of what it is. Questions? Okay, then. That's about it for today's lesson. So